I'm now ready anytime.
Okay, right. Well, in that case, if I can just first of all say the usual greeting, good morning, good afternoon, good evening, wherever you are, wherever you're joining us from, anywhere in the world. And welcome back to OSMU 2025. I'm afraid I've forgotten what number in the series we are. I think it's number 10 this week. Anyway, today it is my very great pleasure, very great personal pleasure, to introduce today's speaker, who is Bob Coecke. Bob did his PhD at the Free University of Brussels in 1996 and then joined the theoretical physics group at Imperial College in London in the days when it was under Chris Isham, and then subsequently went on to work at McGill University in Montreal with such luminaries as Jim Lambeck and others, and many of the leading figures in category theory, of which Montreal was then very much a world centre. And later in Cambridge at the Department of Pure Mathematics and Mathematical Statistics, and then at the Department of Computer Science at Oxford, where until 2020 he was Professor of Quantum Foundations, Logics and Structures. And since 2020, he has been the Chief Research Officer of Quantinuum, formerly Cambridge Quantum Computing, and he is also a Distinguished Visiting Research Chair at the Perimeter Institute. He pioneered the whole subject of categorical quantum mechanics. In fact, he has the first entry in the mathematics subject classification index for that subject, for that topic. And he has also been at the center of applications of category theory to the modeling of natural language and to natural language processing. He's a founder of the quantum physics and logic community and of a whole series of conferences going back to the early 2000s. And he is also today the editor of the journal Compositionality. In his spare time, which you may be amazed to find he does manage to somehow create for himself with all of those other commitments, he is very interested in industrial music, and he is one of the pioneers of the applications of quantum computing in music. And today he's going to talk to us about the work which at the moment is very much in the forefront of his attention and activity, which is the development of new tools for teaching quantum theory, quantum picturalism, a new language for quantum. Bob, over to you. We usually speak for an hour or so.
Thank you, Mike. Thank you, Mike. Maybe I'm going to... So yes, this talk will have two parts, as the announcement suggested, and I kind of chopped it up in two. But I want to say something special here first. So I'm sitting in my music studio to start, and it's bloody hot here in the UK at the moment. We're in a heat wave. And I got like colleagues from Morocco who work for me, from Pakistan, and they say 40 degrees Celsius or 45 degrees Celsius in Pakistan or Morocco is nothing as compared to 30 in the UK. It's much worse, this 30 in the UK.
True, because it's so much more humid. They're quite right.
It's the humidity here.
Yeah, agreed. It is much worse.
Then I wanted to say something about one of my hosts. Wait, I don't know whether you can see this, but I've on the left here, I've got a poster. Is this on the screen? Can you see this? Yeah?
Not yet.
No?
No, you can't see a poster yet.
No?
We just see your title page. Quantum Picturalism.
You don't see me. You don't even see me.
No, we just see your title page. Quantum
in the little. You don't see me in a little corner or anything. That's
we see. Yep. I see you.
Oh, well, that's because I switched off that. No, yes, we do now. We see you in the bar above. Yeah.
Okay. So there is this poster. You can't read it because it's small. But it's a conference Mike organized in 2003 in Florence, and I mean, there's lots of stuff in front of the list of names, but like you had Levere, Pierre Cartier, Dana Scott, Andre Joel, Angus McIntyre, Peter Johnston, Colin McClarty, Martin Hyland, Marta Bunge, and he goes John Byers, and he goes on. That was not the end of the other names are hidden behind my list. So it was like the crème de la crème of category theory. It was an entire conference set up by Mike in Florence called Ramifications of Category Theory. And as a little kid, Mike had the stupid idea to invite me too, among that list of big names at a time, like in 2003. As it turned out, what I'm going to talk now, the first time I ever even dared to talk to it, something in that direction, specifically at that conference that Mike organized at the time. So the community should be very, very thankful for all the efforts Mike has been doing over the years with setting up the archive. I assume that many people know about this, but Mike has been recording talks going back to the early 70s, or am I wrong?
Is it? No, that's early 1970s.
The early 70s. He has a ridiculous archive of top recordings of all kind of talks and all of that. In more recent years, it's video, transcripts of talk, all of that stuff. And there is now a project going on to try to basically get all of that digitized. A lot of that has already happened, but it's with these sort of things, it's always hard to find official instances to properly do it. So there should be some kind of community effort to get all of this in place for at some point and host it somewhere. I don't think it's going to be too hard, but it needs to be a community effort. I mean, that's the first thing I wanted to talk about. So specifically about Mike Wright. Okay, let me now go to the talk. So the first part is called Quantum Picturalism, New Language for Quantum. I should say, when I talk about language, I mean something more than language. To start with the talk, what do we mean by the language of quantum? What I mean by the language of quantum is whatever von Neumann made of it. I know there's a lot of focus now about Heisenberg being the father of the quantum formalism, but really, I mean, Heisenberg didn't even know what a matrix was, to be honest. So you can hardly call him the father of the quantum mechanical formalism. That was like Jordan and and Bohren, who basically got a bit of matrices in there. And of course, von Neumann understood that this was actually not just about concrete matrices, but that was the algebraic structure of Hilbert space that you needed, and that basically is still the way quantum mechanics is now being taught. In the von Neumann language, he came up with density matrices, and all the quantum mechanics is not saying, okay, we got a vector and we got linear algebra. No, there's a lot more to it, of course. There's the fact that you use density matrices, the projection postulate that happens in measurements, all of that stuff, and a lot of that was brought together by von Neumann, of course. I mean, the use of tensor product was also, of course, of key importance. I'll go to that later. But so that was all brought together by John von Neumann. So I would say John von Neumann is the father. It's just a little bit hard to pinpoint the precise date when that happened. But this was all put together in his book from 1932, Mathematischen Grundlagen der Quantenmechanik, in which basically he laid out quantum formalism fully. That was also the start of quantum foundations, in the sense that he had the first template and statement of a hidden variable, no-go theorem for hidden variables. So there was so many dimensions there going on. And there were already the first indications that he wasn't entirely happy with his own formalism in 1932 when he publicized it, because there was already a strong focus on projections and the structure on projections and what it can give to you. But then going a few years later, 3 years further to 1935, we are now talking, a letter, I think, to Gerrit. He wrote to Gerrit Birkhoff, the lattice theoretician, and he said, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So he basically denounced his own brainchild, his own quantum formalism, 3 years after he wrote a book about it, which is pretty much can be used today as a textbook. There's nothing wrong in it. It's all, I mean, some things should have been probably some extra notes and stuff like that by now, but essentially the formalism is still as what people teach it to be. So what happened then? What happened then is with Gerrit Birkhoff, he wrote a paper, which a lot of people know about probably. It's called The Logic of Quantum Mechanics. And that's where he introduced the thing which is now referred to quantum logic, which was worked on by many people. Many smart mathematicians worked on that, like for a very long time, till close to the end of the previous century. But now I think the status of quantum logic is that it's still used, but not in physics. It's used in things like modeling, in psychological, experimental psychology, and some things like that. Some sociological uses, where there are some quantum phenomena, which are bloody obviously present, and then the structure of what he called quantum logic, which is really a little bit like propositional logic, like standard propositional logic, but you just drop some axioms. So instead of saying what's specific to quantum logic was saying something that fails in their mind in quantum. And that's a negative statement is usually not very helpful. And that's why pretty much I think quantum logic is not used anymore, except in fields where people don't really know yet what's going on effectively. Anyway, so how did von Neumann get to quantum logic and this idea of formulating it? By the way, he denounced that himself too after a while, quantum logic. So it's not that that he sort of stayed with that for the rest of his life. No, that he denounced too. There's not many scientists to do that, denouncing their work time after time after time, because they realized it wasn't really right. Anyway, so the motivation to go to quantum logic and whatever, and some other things that von Neumann did after, was what happens to a quantum system when you measure it, when you try to observe it. So when you do an experiment and try to get some data, then as people probably know, then the state of the system changes. It's not the state you start with anymore. If you do an observation, it changes, what people call the collapse. There is some non-determinism here going on. And that basically affected the idea, how can one reason about observable properties of physical systems? Because observation is such a mess that whatever properties we assumed since Aristotle about axioms we assumed since Aristotle about observational properties, they didn't hold anymore. And for example, the deduction theorem and anything like connect to that in whatever way logicians have formulated it, that breaks down, and that pretty much kills a lot of the things you actually use logic for in the first place. So anyway, so that was kind of a failed project, but the thing to remember here is the focus on measurement as the thing that von Neumann was trying to conceptualize, going first in quantum logic, then in things like von Neumann algebras, type 2 factors of von Neumann algebras, things like that. So I mean, von Neumann tried a lot of things to make quantum formalism different. In the process, he invented a bunch of new fields of mathematics, which are all very useful, but not necessary for the intended purpose. Okay, Schrödinger, now I bring up Schrödinger. So why this rent I just gave you? Well, Schrödinger, of course, known for his cat, is known for his equation, but then something he's probably less known for.
Bob, I do apologize for interrupting, but should we not be seeing your slides advancing? We're still on your title page.
Are you?
Yeah.
How is that possible?
Don't know, but we are. We haven't actually seen them advance on the title page. Yeah.
Oh dear. You don't see any advance?
We do now. Now we see a picture of von Neumann. Now we see the, but we're only seeing those for the first time.
Yeah. Wait, that's weird. That makes no sense. Full screen mode. Are they now advancing?
Not at the moment, no.
They were advancing.
They're not. Okay, then I'll stay with the other screen. I don't know whether there's some.
Now they're advancing.
Yeah, I think there's effectively something wrong with my computer, like I said at the beginning.
Yeah.
And I think this is heat related. It
could be, because you seem to be in a loop. We're seeing the screen, the title page,
and now it's
the language of quantum, then a photograph of von Neumann. It's now the quotation that you, and now we're back on the title page.
All I'm doing is going to full screen, and then it stops loading, which it shouldn't do, obviously. So I'll try one last time, but it doesn't matter. So it's not moving. No, obviously.
At the moment.
Okay, so that's weird because it's moving.
Now we're seeing a thing that says.
Okay, let me just stick with this one then.
Okay,
that's weird. Anyway, so that was the title page. So I talked about the quantum of language. I mentioned von Neumann.
Correct.
Let me go through this statement here. I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more, which I talked about, right?
Yeah.
And now Schrödinger. Okay, good. So we didn't miss much on slides anyway. We didn't miss much. So Schrödinger is known because of his cat, because of his equation. This is something that, well, at least not until recent, Schrödinger is not that known for. But Schrödinger said, and this is in contrast to what I was just explaining about von Neumann, that when two systems, of which we know the states by their respective representatives, enter into temporary physical interaction. What he basically says is, you got two systems, and you're trying to look at them together. That's it. Nothing more. That's what we would say in human terms. You got two things. Let's call them objects to be super provocative. And then we basically observing them at the same time. And they will, since they're in the same place, they will interact some way or another. For our typical objects, there's not too much interaction. But for quantum systems, there's a lot of interaction if you just bring them together. And that's what people refers to as entangling. And so they will likely get entangled in some way or another, because it's very hard to keep something not entangled. At the same time, if you, it's just very hard, whatever you want to do. Yeah. But anyway, he says then, I would not call that one, but rather the characteristic trait of quantum mechanics. So this is in contrast with what von Neumann was just saying, that he thought that the key characteristic trait of quantum mechanics was quantum measurement, was quantum observation. If you have gone to any philosophy of physics seminar in the last, I don't know, I mean, for as long as you lived, I think for everybody here in the audience, for as long as we all, each of us lived, the majority of people are talking about stuff like the measurement problem, this, measurement problem, this, always the same story. Always about the measurement problem, as if there is nothing philosophically worth discussing about quantum mechanics than quantum measurement. And this is very much in contradiction with what Schrödinger claimed here, that it's actually, according to him, what we call entangled, what is about bringing systems together, that is the key characteristic trait of quantum mechanics. So that's a big departure from the culture that has been around for a very long time. Yeah? So that was Schrödinger's idea. Okay, here we got Roger Penrose, who I think he has spoken or will be speaking in this series. Am I right? Yeah.
Yeah, he has spoken. He has spoken.
Okay. So Roger, also, I'm based in Oxford still, by the way. So he's also based in Oxford in mathematics. I'm still teaching in mathematics in Oxford and supervising. So this is Roger, who's known, of course, for black holes and stuff like that, for which he got a Nobel Prize, for Escher drawings and things like that related to tilings and all of that. Again, something is probably less known for is that when he got an undergrad, when he had to study at university relativity and had to sort of deal with this kind of tensors and stuff like that, he didn't like them. He didn't like the symbolic notation on the left. Instead, he liked these pictures, and I sort of indicated here. So you got your big symbol, your tensor, and then your subscripts and superscripts. And you can actually write them, for example, like a blob, which represents the tensor, and then wires in and wires out, which represent subscripts and superscripts. So he preferred much more, he introduced that notation as a way to draw tensors. When he was an undergraduate student, I think this first appeared in a paper as nothing more than in an appendix, I think something about negative dimensional tensors in an appendix, that you could have used this alternative notation, and very little was done historically at all with that. It was completely unknown, given there was like an appendix of like just one paper somewhere from 1971. This kind of changed it when category theory came into the picture, because people like André Joël, Street, going back to the Australians like Max Kelly, also Bob Walters, people like that, they kind of like this graphical notation because there's a lot of mess if you do. I don't know how many people here are familiar with category theory or monoidal category theory. There's so much mess there if you try to formulate things algebraically. And this is to do with things which are called non-strict things. What does it mean for non-strict things? Well, if you do set theory, A, product B, and then product C is not the same set as first B, product C, and then you put A, product B, product C. That's not the same set because everything is paired differently. Now, for every practical purpose where you're actually talking about a triple, you want these things to be the same. You want them to be treated the same. And then you have to introduce like a monster called a natural transformation, a natural isomorphism. And that's actually why Eilenberg and MacLean invented category theory in the first place anyway. So what these pictures do is they get rid of all this sort of bureaucratic nonsense you inherit from set theoretic basics. and which create an incredible mess about your mathematical formalisms. So that's one reason category theoreticians like them, because it made things so much easier just when you're thinking about monoidal categories. So they like these things. And then since the 90s, they became quite more prominent. Some computer scientists started to look at them, pick them up, because there was a way to think of processes in these sort of monoidal category theory terms. And so slowly, these kind of pictures were not complete obscurity anymore. Well, they were still pretty obscure to your average scientist, not to say utterly obscure and non-existent, but there was some literature started to emerge late 90s, early 2000s, mainly around people who had something to do with computer science in some way or another. Okay. Now, so I mentioned three things. Let's summarize. We had von Neumann talking about quantum languages and quantum formalism, Schrödinger talking about composition, Penrose talking about pictures. Well, drawing pictures, let's say. So von Neumann wanted new quantum formalism. Schrödinger said quantum is all about composing stuff. Penrose uses pictures instead of symbols. Turns out the two last ones are one and the same thing. So focusing on composition as your main primitive of your formalism or your language or whatever you want to call it, as your main conceptual foundation of maybe the world, like the biggest primitive we have is sticking stuff together, and drawing pictures in the sense of Penrose is one and the same thing. So the pictures literally incarnate the idea of taking composition as your first-class citizen in your language. So here is, and now I'm going to go a few steps further. Okay, here is Quantum in Pictures. That's a book which I publicized in early 2023, I think. Yeah. So what is this? Well, I'll just say what it is, and then I'll say a little bit how we got there. So what it is basically a formulation of quantum mechanics in terms of pictures. They're completely different from what Penrose intended to do, because he was looking at relativity theory and all that, and they required a lot of different ingredients, and I'll explain some of them. But yeah, it's essentially quantum mechanics in pictures. And let me read what's on the back. Hello there, want to learn some quantum? Maybe you think you don't know enough maths. Well, that's not a problem. The pictures in this book are a new kind of maths that will teach you all about the quantum world. And this is really like a full-blown book. You find like things in quantum foundations, like proofs of non-locality, quite sophisticated things like measurement-based quantum computing, which you don't find in standard textbooks. But you don't really need any particular mathematical background to go through this. And I'll give I'll give experimental evidence for that fact. Now, I think it's probably worth saying how we got there. Around 2002 to 2003, I start to see, and I didn't know about this pictorial language, by the way, at the time. I mean, it was not something that was at all like at the forefront, but I start to realize that there are things in quantum mechanics you can understand by drawing wires, by just drawing wires instead of writing matrices. I mean, the thing I had in mind initially was something like quantum teleportations and some more things, how you compute your probabilities, things like that. And so I started to draw wires. And then a year later, with Samson Abramsky, we wrote a paper which is called Categorical Semantics of Quantum Protocols. We axiomatize this in terms of monoidal categories. We axiomatize this in terms of monoidal categories. When we came out with that, there was such a cynicism and blah, blah, from so many communities, especially like theoretical physics community. But last year we obtained a Test of Time award. And that's actually the first Test of Time award across computer science conferences, quantum and no classical computer science conference that was ever awarded for quantum. So we must have done something good. Anyway, that paper, lots of work, lots of new concepts emerged in this, what is now a way to formulate quantum mechanics in a way that pretty much everybody can understand if they want. You don't need to go to university. You don't need to learn the fancy maths. A lot of stuff is already here. So that's the thing we did. I should say, like, for example, I think we can go a little bit broad in this seminar. Sociologically, it was very interesting to see the reasons people basically didn't want to go on this boat. On the one hand, you had people saying, this looks too simple. On the other hand, there are the same people were saying, this is too complicated. So they were saying everything at the same time. And then, okay, well, what can you do? What can you do? Well, wait until they die. That's what Max Planck said. In order to come up with a new paradigm, a new scientific idea, don't try to convince your colleagues, just wait for them to die. That's what Max Planck said, the father of quantum mechanics. Well, the initial father came up with the idea of quantum, about like, yeah, what they had to do with quantum altogether, just waiting for people to die. So, okay, we did that. Now these people are gone, so we actually are much more successful. Let me move on. Yeah, like one-page article in The Guardian, because we did an experiment. We did an experiment in summer of 2003, I think, if I remember well. Yes, summer of 2003. I'll explain what we did in the experiments, what the sort of ramifications are of that. And but it was important enough to warrant like a page in The Guardian at the time. Unfortunately, at a date that nobody reads anything, like December, not too long before Christmas. So that's like unfortunate, but okay. So these are experiments that I'm going to talk about now. Okay, so we had this book, and this book was essentially written as a textbook for a course. A textbook for a course. We have lectures for the whole book. So we set up some lectures. Here you can see a screenshot in my office. So it's not just a book, it's also a whole lecture series. They are online available. We haven't advertised them yet formally, but if you look carefully, you'll find them online already. But soon they'll be advertised in a much more prominent way. We made exercises, exercise sheets, exercise solutions. So essentially, these three ingredients are sort of standard ingredients of a typical Oxford University postgraduate course, as probably many courses. But we did it such that we had like 8 weeks of material, 8 weeks in the sense that every week you had to watch a lecture, one lecture, which is a video. You, of course, have the material written down in the book. And then you got an exercise sheet, which you had to try to solve. On top of that, there was like 1 hour, one-to-one interaction with a tutor. 8 weeks. Why did we make it that shape? Because we actually wanted to give the students a summer course. So we send out flyers, learn about the quantum world in pictures. This was like June 5, August 13. Not entirely ideal. Some were like still working on their A levels. They go on holiday with their parents. We sent this around in the UK. And we told everybody, if you take this course, you get a certificate from us, and it's going to look very good, signed by Oxford University, signed by Quantinuum. We also had some help from IBM. So it's going to look really good in your university application if you just take the course. No obligations, no stick, just a carrot. Just a carrot, no stick. Huh? We got 1,000 applications, and they looked very, very mixed. I mean, because we did ask them information about how well do you typically do at school, and how confident you are with sciences, things like that. And it looked like a pretty random cross-section of people in the UK. And we couldn't do the course for 1,000 people. So we sort of went down to 70-ish, which in the end, I think 65 ended up finishing the course. Some just dropped out, and they said so. So yeah, 70-ish start, 65 say. And then we run the course over the summer during these dates. Now, by the end of the course, we asked the students, hey, can you help us? Because it's actually all for a research project. We want to understand how we can better teach quantum. So it would be good if you give us some feedback. And this feedback will be given in the forum that we will ask you to do some exercises, a few more exercises, and then you just send them back. No consequences. However you do, no consequences. Like I said, you'll get your certificate anyway, however good or bad you do. It doesn't matter. Huh? So they did it. What they didn't realize is that all the questions we were asking were questions from Oxford University postgraduate exams. So questions that had been asked in postgraduate courses at Oxford on quantum mainly the space of quantum computing, some quantum foundations in that space. Yeah? So they didn't know that. So so we had these kids who were basically measured against, in some way, Oxford postgraduate student. Like I said, we actually made a random selection of these, coming from public schools, coming from state schools, all mixed, ethnic backgrounds mixed, north of England, south of England, everything mixed up. So they got an Oxford postgraduate exam, and 50% of them had got a distinction, which is higher than your typical distinction rate in typical Oxford University postgraduate courses. So that was even surprising to us, because it was a very difficult experiment to run. One thing you should realize is this was a very special generation of young people, because they are the ones who were like at their puberty during COVID, which of course is quite a life-forming experience. And we could see this that they all never put on their face. It was always black screens whenever there were tutor sessions. They never asked questions, they typed questions. And it was very hard to break this, because I wrote an email. I said, okay, we want to learn how we can teach this stuff. So please give us feedback by facial expressions, by the tone of your voice when you ask a question, all these sort of things. In the end, I mean, one person then put his screen on for 3 seconds and then put it off again, because that was peer pressure, you know. So that didn't help much. But the results were overwhelming. Like overall, we had like, I think, 80 plus passes. And then we had something which is called the canary question, which is a question in which you could see, it was so simple that you could see whether somebody made any effort at all. And so it was clear that of those who actually made an effort, such a big majority actually passed. There were clear differences. Some were very good, others just worked very hard. No, not perfect, but they made a decent effort, and there were some sometimes silly mistakes and all of that. But overall, the majority just passed. So that's a statement about like how easy it is, or whatever. I mean, I'm going to qualify the statement later, to use this new language of quantum as compared to the usual one for a broad audience. I think I got some tables here, yes. So the first table, I mean, the first thing on the top left, prior knowledge of quantum. So the majority knew nothing. Of course, there were a few people who were advanced, like 6-7%. But the other ones like was quite limited knowledge of quantum. Let's go down.
Just curious, a quick question.
Yeah, perfect, of course.
Yeah, so this formalism, which looks very interesting, does it cover only the Schrödinger evolution part, or also the measurement and collapse?
It's almost the other way around. It is all about the measurement. It's all about like composing systems. It's about like Schrödinger is there too, but in the form of quantum circuits, for example. We can do Schrödinger explicitly with differentiation, integration, exponentiation, but that wasn't included here. That part wasn't included here, but you can do that. But this is the version which mainly supports what you would do if you do quantum computing or quantum foundations.
Okay, get it. Thank you.
And you see that. I'll give some examples. You'll see that. So another remarkable thing is how little time they put in it. The majority did 2 hours a week. I mean, it was very hard to see how they did it, because the lecture was like 1 hour and it was 1 hour tutoring. So, so it's hard to, but they probably didn't, maybe they thought, okay, we did 1 hour extra or something like that. Maybe that's what they intended. You see, it wasn't a big effort they put in altogether. So top, right, the course strengthened my motivation and confidence. Vast majority agrees. The course motivated me to pursue STEM career. Vast motivation agree. Before the experiment, we explicitly checked whether they were particularly focused on science or other things. And again, we took some sort of cross-section there. So it's not that these were per se people who were interested in a science career at all. So that's nice. And then the table below, you see, these are different kind of schools, state school, grammar school. That's a typical English thing, if you don't know, private and boarding schools. The results were all pretty much around 60 on average. No real difference between sort of the background from the schools. And that's because this was all from scratch, pretty much. This was not about what you've already learned at all. Okay, so one question I didn't put here, which I think is very important, we had some sort of more open-ended question, which was asking just for a comment, what did you appreciate the most of this course? Could expect answers like, oh, that was interesting, that was like that will help me in my career, stuff like that. No, the majority answer was it was fun. And that's very important too, that whatever you do in life is fun. Not just like, now I can show off, now can I show off to my friends or something like that. Okay. Right. So I mean, a lot has happened since then. So and I'm just focused on a few things, like probably the most important things that in Greece, they are already teaching now quantum in this way in high schools. And this went with governmental approval and all of that. So that's already happening. That already took place like the past year. And they're going to increase that the next year even. Colorado is also very fast moving into like implementation at the high school level of these things. We're going to set up a much bigger experiment there very soon, in which both Denver public school system and the Air Force Academy, who's also based close to the Denver, will participate. So there we're going to effectively have a comparative sort of study, Denver public school kids against Air Force Academy cadets, which is going to be fun. And then quite a few other things are going on, translations. For example, there is at the moment also Ukrainian. I mean, this slide is old. There's like a Ukrainian translation is almost finished, will also be published. So quite a lot of things are going on around this now. I mean, I should say like this was a very big effort with lots and lots of people involved, from Quantinuum, from Oxford University, mainly computer science, also from physics a bit, and then some other people. So yeah, it was a big effort with a lot of people involved. Right. So let me now go to what this language really is. And now, of course, I don't have that much time, but that's maybe a good thing that I can do it very quickly. So the whole idea is that you think of things in terms of wires and boxes, which is really like, this is like the way to represent the category, by the way. You got a box is a morphism from an input wire to an output wire. So from one object to another object, that's really what it is. And then plain wire is like the identity for that object. So this is really, if you know category theory, this is really what it is. There's nothing more to it. But in the way that you get rid of all the sort of bureaucracy from set theory. Anyway, this is your category. Now we want to do a little bit more than just like composing boxes one after another. We just make this kind of networks with boxes. We compose them together like this. So that's basically the operation you can do on wires and boxes, make network. Think of it as a flow chart. Think of it as something like tensor networks, if you want to. It's something like that. It's a monoidal category. It's we treat it as symmetric because the swaps won't mean anything. Now the important thing is like at this point when you draw pictures like that, you see I drew something there which are two wires side by side. What does it mean to have two wires side by side? Means you've got a system of two things. That's why I'm saying these pictures are the same as taking composition of systems as your first class citizen. Because the first simplest thing what you can do is draw a diagram like that. There is this idea of composing systems. So we think of these wires as carrying particles if you want, maybe photons, electrons, anything like that. I'll give some examples later. It doesn't matter. But the important thing is that at the very start, you're already composing systems. You're putting systems side by side. Okay? You can fill these boxes now with whatever you want. This can be electricity. I mean, we all have electricity wires and electricity boxes and all of that all around our house. We can do lots of stuff with it. We got water systems, for example. We, of course, have like computer systems all in our house. So these are all just examples from the same thing. And that's where you compose devices and stuff together, like a cooking recipe. Just a cooking recipe is another example of this. Huh? So this is such a very general template to cover stuff. So you can ask yourself, okay, what should we fill these boxes with if you're going to do quantum stuff? I mean, of course, quantum systems, that would one way to answer. But like, let's now become a little bit more mathematical. Like, what would be the sort of more basic structure we can fill it in? And we want to stick to pictures. So we want to fill these boxes in our pictures with pictures themselves. Now, what kind of special pictures will take us into the quantum world? And that's a concept we call spiders. Now, I don't know how many people here in the audience know about quantum algebra type structures, or yeah, maybe a lot of like Strailing category theory or something like that. But I'll explain what they are, like in very simple wire terms again. So what is a wire? So the idea is to generalize the concept of a wire. Wire is a very simple thing we can easily understand. And what is a wire? A wire is a thing which has two endpoints. Yeah? Wire is a thing which has two endpoints. Okay, what can you do with wires? You can connect two wires together. There's much more you can do with wires. Well, you could actually like connect a wire to itself, and then okay, there's not much use. Then you have a hula hoop or something like that. But in general, you can just connect wires together. If you think about an extension lead, you take two extension leads and you still have an extension lead. So what are these spiders? They're very much like wires, but instead of two ends, they can have multiple ends. I mean, here it's 8, but it can be any number. Can be 1, can even be 0. Doesn't matter. And if it's 2, it's exactly a wire. It's like a wire. Yeah? Now, what can you do with these spiders? Well, they're a generalization of wires. So if you connect two spiders, you get again a spider. It's very simple. Very simple rule. Very simple rule. And now I want to take a little break, and I'm going to deviate a little bit. What you see here is the definition of an orthonormal basis, which may sound confusing and completely unrelated, but if you interpret these spiders as living in a Hilbert space, if you interpret these wires as, say, Hilbert spaces, and two wires side by side as tensor product of Hilbert spaces, then this equation forces these spiders to be in one-to-one correspondence with orthonormal bases on that Hilbert space. I can't explain this. This is a highly non-trivial theorem, but this is how this connects to the usual quantum formalism. When you see a family of spiders like this, which fuse together like this, then you have to think in the back of your mind, but not too much, not in the front of your mind, vaguely in the back of your mind, as I'm seeing an orthonormal basis here, translating to quantum, I'm seeing an observable here. I'm saying a quantum observable here. You'll see later how this works. You'll see later how this works. I just want to give you some connection already at this point with the usual Hilbert space formalism. What's being formulated here is the equivalent of an orthonormal basis. But of course, you don't need to know what a Hilbert space is. You don't need to know what linear coefficients are. You don't need to know anything like that, inner products. This is it. Just spiders fusing together. That's all you need to know. To have the equivalent. Okay, so the spiders fuse together. So that's one simple thing. Now, when I talk about like an orthonormal basis or a quantum observable, in quantum mechanics, you have more observables than one. Like the typical example is position and momentum, for example, as two possible observables. So we'll need two of the spider kinds. We need two kinds of the spider. When those of the same kind meet each other, they fuse together. And it's a big love story. It's a big love story. When two of different kinds encounter each other, it's not at all a love story. They both give each other like an uppercut or something like that. And then these legs fall off. The formal rule is when two spiders of different colors are connected by two wires, then these wires vanish. Two, by the way, is crucial here. And what they base, if you think of these spiders, again, in the typical formalism terms of orthonormal bases, this means that these two orthonormal bases stand in a very special relation to each other, which technically is referred to either as complementary or mutually unbiased. So they stand in a very special relationship to each other. They're as far apart as possible from each other. That's essentially how you should think about it. They're as least connected to each other as possible. So again, we got the spiders, same color, they fuse, different color, legs fall off. That's enough now to actually start to do some quantum computing stuff. You don't need anything more. So we're going to do some computations with what's called the quantum program. This is really like a unitary circuit. So what you see here is a quantum program. How should you think about it? These 3 lines, they're qubits, they're quantum systems. Well, I should have said, we conventionally read from bottom to top, but you could as well read from bottom from top to bottom. But conventionally, I'll try to explain everything from bottom to top. So these are 3 quantum systems, 3 qubits. These are 2 gates, like think logic gates, which you apply each to 2 of these 3 qubits, like first one to the first 2, then one to the second and third, and then one again to the first 2. Very simple operations. For those, again, who are familiar with quantum gates, it turns out that for the canonical choice, really, of what the green and the red dots are, they're C0 gates. They correspond with very important gates in quantum computing called C0 gates. But again, it's not important for the calculation which we're going to do. Now, okay, so this is a quantum program. We want to make this smaller. How would you do that? The first thing you do is whatever I just told you about C0 gates, really blatantly forget about that. Just think of this as a bunch of spiders, nothing else, as we started. So, okay, the audience, I'm now going to ask the audience, you remember the rules about spiders? There was only 2, so it's not too difficult. So what is the first thing I would do now to simplify this? Give you some time to think about. You can say it if you want to. I can go back. Same color fused together. Different color, 2 wires in the middle vanish. 2 wires being important. Do we see things of the same color here? Yes, we do. Wait, let me go. Yes, this.
The 3 green become 1?
Yes, and the 2 red become 1. That's just following the rules. 2 wires between red and green, they vanish. Now we see on the left the spider with 2 wires. That's just a wire. So, okay. So this was still a simple calculation using this language, this new way of calculating. What you usually would do is you take the matrices of these things. They're 4x4 matrices over 3 wires. They're not they're now 8x8 matrices. They're quite big matrices, and then you calculate what it does. But that doesn't even teach you much about how you would simplify per se. So it's a completely different game here that's being played. Very simple. I'll go through it again. Because, okay, here you got this one. These in principle are 3 qubits, 3 C0 gates. Forget about all of that. Fuse the things which are the same, which are this. The 2 wires go away between a different color, which are this. And we start with the idea that two endpoints just mean white. So this example, which I just explained to you, is now the state of the art on how you simplify a quantum program. You use the spiders. That's the state of the art.
Could you please explain why this is like quantum mechanics and say not like classical mechanics?
Very good question. Very good question. And a bit of a trick question. No, this in principle could be applied. The example I just gave you could in principle be applied to classical logic gates because a C0 gate can be classical on bit. This example I just gave, indeed. And I'll say later how things become quantum per se. I just wanted to give you an idea of the calculation, and I gave an example sneakily, which is as much for classical circuits as for quantum circuits. So good question. So I'll get back to it. I just want to say this with the additional thing I will teach you in a bit is now the state of the art on how you simplify quantum circuits, proper quantum circuits. If you go to a compiler or something like that, or an optimizer, in quantum computing companies, this is how they simplify. So the thing which I first explained as a medicational tool is actually also a very important engineering tool now in quantum computing. Also in error correction, this is very widely used. So this method is now very widely used in quantum engineering. Very important question, what is different between quantum and classical, which we're now going to go into. So, yeah.
Bob, what happened to your red circle on the left side?
Oh, okay. So I said like a spider with two wires is really just a wire. Remember, a wire has two endpoints.
Okay, all right, thanks.
So it's just a special case of a spider, a wire, if it has two endpoints. Yeah. Okay, quantum versus classical wire. I'm saying ordinary because classical is such a confusing word. If you're not trained in quantum theory where they actually use this in a particular way, which is not the way people use in the modern way. When you say classical, they think about classical music and stuff like that. A completely different thing. So we should just say ordinary. Okay, this, I'm going to explain something. This is actually something von Neumann already knew, implicitly at least. From now on, and I was being sneaky, as I admitted, we're going to draw quantum stuff as a double wire, not a single wire, as a double wire. And classical data and classical circuits, what you want as single wires. So now there is an explicit difference between the two, and we want to use them in the same pictures. And what you see here is a spider with two wires coming in very close to each other. We have to treat them as one. We need to indicate, we put them just close to each other to say, actually, there's really one wire consisting of two of these things. Call it a thick wire or something like that, or a doubled wire. And this is a single one. And actually what these represent is the passage from quantum to classical, which means this is a measurement. This is a quantum measurement. We are not talking about self-adjoint operators with spectra of projectors or anything like that. This is it.
Yeah. We've seen this collapse of a superposition.
We're going to see all of that. Yeah. That all is implicit in the rules. The rules I gave you, the simple fusion rules, it's all already implicit in just this representation of a measurement. It's all here already. You don't need to know anything about projection operators. The projection postulate is built in here already without doing anything, without making any effort. And let's give some examples. So, so this is a measurement. This is the dual of a measurement. For example, you got a 0 bit and you encode it as a 0 qubit. You take a classical system corresponding to bit 0 and you encode, which experimentalists do all the time in laboratories. They say, okay, let's encode some classical data as a quantum basis or something like that. That's what this is doing. That's what this is doing. So we've got these two operations, and now we're going to start playing with them and proving things. Okay, this is the simplest one. I encode a bit in quantum basis or something as quantum data, and then I measure it. So what do you expect the result is? This is this. If you want to think in terms of Hilbert space, this is the same basis. You encode in the same basis as you measure. I should say that, of course. Same color. Well, of course, it's the same as doing nothing. Because you encode as an eigenstate and then you measure. So it's the same as doing nothing. Maybe just get this from the fact that these two green dots fuse together. So you don't have to know this. This is just the two green dots fuse together, and then the dot vanishes like Alex asked about. And so we just get from the calculations that this is an identity. More interesting is you encode, for those who know the terminology, say in the 0-1 basis or the Z basis, and then you measure in the X basis. So now we don't encode in the same basis as we measure anymore. What do you get? Two wires in the middle, they vanish. What does this mean? This means that there is no connection anymore, and you can see this from the picture, of what goes in and what comes out. They're disconnected now. And basically what this concretely means is that what we get at the other end, at the top, is randomness. Whatever the data, the state was you begin with, it doesn't matter. What comes out is just randomness. And this, of course, is something you can prove in Hilbert space if you want, but here you get it from the pictures. Yeah, I hear the question.
Is this decoherence?
No, we're gonna see decoherence. It's close. It's close. It's close. Actually, okay, I'll explain what decoherence is later. Decoherence. This is literally you encode. Okay, let me be concrete. You encode, say, in the zero state, and then you measure in plus minus, which means that what you get is randomness. 50% plus, 50% minus. And it doesn't matter. It doesn't matter what state you encode initially. It doesn't matter because you encode in like zeros and ones, and the zeros and one will give you 50% probability for each outcome, whatever the amplitudes are. It doesn't matter.
You're measuring in a basis different from the one in which you
exactly, and not just any, like as far as apart, what they call mutually unbiased.
Yes.
So there's no information flowing from the encoding in one to the one you measure. This is the foundation of quantum cryptography. This example. This is the foundation of quantum cryptography, that you can see if an intruder picks the wrong basis to measure, that it just generate noise, and you can see it then. So quantum cryptography is all based. This is the only picture. These two pictures are really the only pictures you need to understand, like the first quantum cryptography protocol. You just need to tell a bit more story around it, but it's nothing more than these two pictures, quantum cryptography. So in our book, we explain that, by the way. In our book, we explain quantum cryptography with just these pictures. Here is a more interesting example. So, I mean, you see here these green dots with two wires coming in and two wires going out, and then one single wire coming out. What this actually is a measurement where you don't destroy the system. So you start with a quantum system, you measure it, you still have a quantum system, but you also obtain data from your measurement, which are the single wires. Yeah. This is where you would expect to see a collapse in the measurement, because you still have the state. So you would expect it to be collapsed after the measurement and not just stay the same. Okay, let's see what we get on the right. You see these two double wires between these dots, so they vanish, which means that your first measurement of the green dot, or in the green color, has nothing to do with your second measurement. And that's, of course, because of the collapse that happened, because of the measurements going on. So this phenomenon of collapse is all implicit already happening here. Because otherwise you would just get the same in the first and the third case, if there wouldn't be a collapse. So the collapse, that's what I was saying. The collapse is all implicit already here in what is happening. And you can make, there's so many more examples I could have given here, which more explicitly tell you what a collapse is. So you asked me the question, what is decoherence? I don't think I've got the picture, but decoherence would be the case where you do this, the first measurement here on the bottom, you don't care really what your outcome is, and then you look at your state, and your state will be decohered. And you can, again, look in the calculations that that's really what happens. So it's in our book. We have decoherence in our book, and it's just one of these things you see here. It's again one of these things you see here. Right. Okay, now a more important question is
there's a question from the audience, please?
Oh yeah, please ask questions whenever you feel like.
I have a question. So I think the audience may be confused this with decoherence, because there is no picture about what quantum gate can do exactly. For example, when we establish the qubit in zero state and then apply a Hadamard, and then now it's in a plus and minus basis. Yes, there is a loss of information, but
that's not decoherence. So
it's
if
not
yeah. Any circuit, any gate you refer to, Hadamard gate, whatever, these are reversible gates.
Yes.
They're all reversible. So there's no decoherence going on. Decoherence goes on when you do a measurement or you couple to the environment or something like that.
Yes, that's what I understand, but
So let me explain
i-
something. Okay, and I think I can clarify something here that will help you understand. So when it's two wires here,
mhm,
this is like density matrices. So how do you build a density matrix? You take a cat together with a bra, and then
yeah.
you make a superposition. So this doubling of a cat and a bra together, that's the same as the two wires here.
Yes, that's what I was thinking.
Yes, and
In terms,
decoherence basically means that you throw away your off-diagonal elements.
mhm,
And if you would first do this, so you take a quantum system, you measure, you get a classical outcome, and then you encode this classical outcome again as a quantum state. This would be exactly decoherence in the sense of throw away your off-diagonal elements. I didn't have the picture here, but going from 2 to 1 and then back to 2 in the same color, that's exactly decoherence. So you got
exactly.
you need density matrices for that. You're right. You need density matrices for that. And then what the density matrix, what you do to it is you throw away the off-diagonal elements.
Yes.
And that's really just going from 2 to 1 and back to 2. I could have included the picture here, I just didn't do it. But that's what it is. But maybe I should have, I didn't want to confuse people too much by you saying density matrices, but these all density matrices are already baked in here, which is again a nice feature. They're already here.
Yes. Yes, we can feel and the concepts and draw them. So, what if there were pictures of the gates to be more illustrative, and basically any matrices multiplication transform into pictures? For example, with the qubits.
Yes.
Yeah.
Yes, so that's what I want to explain. That's basically what I was going to explain. Like so far, I've used only these spiders, red and green spiders. That's not enough to write down any matrix. You'll immediately, if you know quantum computing, you'll know immediately what you need. You'll need something like phases. You need phase gates. Yeah? The way they get introduced is by decorating these spiders with numbers, angles. They're literally angles. And when you fuse them, the angles just add up. I mean, I've got 99 here, but they can be anything. So that's one sacrifice which we made, and that's the only numbers which we use. When we started writing the book, we were trying to use phases of the moon to avoid, like, almost compulsively avoid use of any numbers. But after drawing 100 moons, we were fed up. It's not the most easy thing to do. So we said, okay, so we've got this picture in the book. We say, okay, you can, if you don't know these numbers, think about moons and then sort of phases of the moon. But at the age of 7 in the UK, you learn what angles are, and you know how to add them at the age of 7 already. So it should be okay, we thought. Anyway, so you add them up. If you take these spiders with numbers here, there is a theorem that any matrix for however many systems, however many qubits to however many qubits, you can write down in this language of spiders. So you got a language that's universal for linear algebra. Actually, technically it's called multilinear algebra because you can tensor matrices together. You can have matrices on tensor products. So that's technically called multilinear algebra. And so any expression in multilinear algebra can be given in terms of the spiders. That's a theorem.
So basically, the relationships between the spiders are the linear algebra operations.
Every linear algebra operation, every linear algebra expression and operation can be expressed in terms of the spiders. Yeah.
That's very interesting.
Including tensor product and all of that. Yeah. And of course this carries over to density like to the mixed state formalism, to density matrices and completely positive maps too. For those who know what that means.
Yeah. So bracket in this example, how can you define the bracket state?
Oh, inner product. You mean the inner product?
I think that's the question, inner product, yes.
Oh yeah, I mean, okay, so Like what in a product between a state and another. Okay, let me go back. So a state, let me go back. So a state really is a box without an input. A vector would be a box without an input. A functional would be a box without an output. And then when you connect the input to the output, the state to the functional, there's no input and no output anymore. So a picture without input and output is a number. So the numbers live this. So if you take a diagram like this and there wouldn't be any inputs and outputs, then it's a number. And for example, like having a state, like a vector, and then having a projection from a measurement, and you want to compute the inner product, that's just connecting them together. And whatever obtained is the number. So all the numbers are representable as these diagrams of spiders.
May I ask a question?
I should probably say, let me say something like, because I haven't mentioned it yet, but like this book, I don't know whether you can see it.
Yeah, pretty close.
Picturing,
Yes.
I've got a slide. Well, let me just go to it. I think I got a slide about that. So for people who are this one, so for people who are really more practicing quantum computing people, maybe, or something like that. So this is a full-blown quantum computing course where you explain everything you would see in a quantum computing course, as well as quantum foundations. And the Hilbert space formalism is also derived from the pictures. So you explain how you work with the pictures, and then you derive basically linear algebra and the whole Hilbert space formalism from the pictures. The density matrices, everything is derived from the pictures, and it is explained how doing something in one looks in the other world. So this is a university course. This has been the course of quantum computing at Oxford University Computer Science since 2012, 2013. And so if you know the usual formalism, this actually gives you a perfect bridge of all the questions, like which are exactly like the questions you're asking me.
Bob, there's a question by Frank.
Hi, I'm invited to talk to a sixth form college near me, and I'm pitching quantum in pictures to them. And I have interest from some grammar schools in Kent. How can I get myself qualified as a quantum in pictures instructor so I can teach teachers at these schools and grammar schools so that we are introducing their A-level students to the subject in a reasonable standard?
Okay, good question, and thanks for asking that, Frank. So we are working currently to basically produce more teaching materials specifically for that purpose, because it's one thing to basically do exactly what we do in the experiment and then teach teachers how to teach. There's a completely different thing than basically just teaching yourself if you already know what you want them to teach. So we're working on that. Arjen, do you know Hamza Wasim? Hamza?
I know Katerina and I know Wissal.
Oh, okay. Wissal can help with that. Wissal is talking to Hamza, and they're gonna work on more teaching materials.
Okay, Wissal and I are doing something for the Royal Academy in Morocco in the near future.
I know about that. I know about that.
Yeah. Okay, great. I will see if I can make contact with Hamza.
Yeah, it's not. He's going to do a whole bunch of lectures in Pakistan, trying to do the same as you just asked for. He's going to spend a month in Pakistan doing the same thing, like teaching teachers and all of that. So materials are being developed.
Oh, this is marvelous news because I have friends in Pakistan too.
Okay, perfect. So you need to get in contact with Hamza then. I mean, let me sort of if I can I elaborate a little bit on the conversation now?
Yeah, please. We have a total of 2 hours,
okay.
including discussion and questions. So you decide if you want to take questions or
Okay,
you
I
want
mean,
to...
I'm already starting the discussion now, more or less. If
Go ahead, please. Go ahead.
so that's what I'm doing. I mean, it's very interesting that there is a lot of interest for this approach. I mean, there's one thing for this approach coming from non-Western countries, where there are different sort of cultural backgrounds and historical backgrounds and just different philosophies and ways of thinking. Because my view on the matter is that a lot of how we teach usually science, be it Hilbert-space formalism or pretty much anything we do in physics or exact sciences, is very much within a very specific way of looking at the world, which has been adopted by the West 2,500 years ago, going back to the pre-Socratics, to the ancient Greeks. So, and this view is mostly associated with people like Parmenides and Democritus. For example, Democritus put forward the idea that we understand the whole by just understanding the atoms and the parts. If you look at physics, that's particle physics. If you look at mathematics, that's set theory. If you look at biology, that's both anatomy and genetics. These are useful ways to think about things, but it's definitely not the only way you can reason about things and think about things, by just looking how things are made up. At the time, there was a big debate, for example, between Parmenides and Heraclitus. Heraclitus' idea was, Parmenides' idea is like there is a static picture all the time of reality. We're always in a static picture, which physicists call kinematics. Kinematics is sort of the static photo we're living in, and dynamics is going from one picture to the next. So Heraclitus' idea is there is constant flux of things, and the pictures I'm drawing, they're like processes. They're like giving that flux. Then, of course, Democritus was more about like, how is a thing made up? Leibniz was, we understand things on how they relate to other things. This is where interaction and composition are coming into the picture. Like I hinted to, like by first referring to Schrödinger and his view that quantum mechanics was all about when things come together. So this picture very much embraces like the ideas of Heraclitus and Leibniz versus, say, Democritus and Parmenides. And we have seen that established scientists sometimes have a much harder way dealing with these pictures than much younger people. We even saw that the 15-year-old did better than the 18-year-old. So there is clearly I mean, this was only English students, so that they all were brought up in the usual Western school system. But the reason I'm going in there is that that you can see that in other cultures. So we've been teaching in Ghana, for example. People kind of really appreciate these different views sometimes more than the typical Western scientists, who want to translate to what they know, and the translation is not easy. So you're actually doing double work or triple work. So I thought that was like a worthwhile comment to give you here in relation to the mention of like Pakistan and Morocco, and I just mentioned Ghana. And there's a lot of interest like from non-Western countries in this new approach.
Yeah, I was just going to ask you, Bob. So of course, this is very enlightening on a certain aspect of quantum mechanics, like what happens during a measurement, for example. Now, let me ask the other kind of question. I want to calculate the spectrum of the hydrogen atom, its energy levels, and teach that to the students. But then I have to go back to the Schrödinger equation, isn't it?
No, it's not. So, I mean, what I'm teaching, so what I'm talking about today is really the level of stuff that we taught to 15-year-olds, 16-year-olds, maybe earlier. Now, if you want to do these sort of things, then you can do extensions of this calculus, which is called ZX. So technically, what I've been presenting is called ZX calculus. If you Google ZX calculus, you find a whole lot of resources about exactly what I'm saying. But there you will also find paper on what's called ZXW calculus, which has one extra kind of spider. And this allows you to do integration, differentiation, exponentiation, and the stuff you need to solve your Schrödinger equation.
Mhm.
And
Uh,
you can Google that and you'll find papers from the last couple of years, effectively, from the last 2-3 years, where all of this is set out, where it's shown how you can basically represent an Hamiltonian as a diagram, then do exponentiation in order to get your evolution and all you need and your eigenvalues and everything you want to know.
mhm.
So you
Okay.
can do that. You can do that. That's
Bob,
very much.
No,
Yeah.
sorry. There's a question in the chat from George Sparling. Conventional quantum mechanics is intimately related to complex numbers and/or the Riemann sphere as a complex manifold. I see no mention of these here, question mark. So what happened to complex
Can you
numbers?
say that? Oh, yeah, okay, yeah. That's what I was actually starting to explain. So with all I've been explaining so far, there's no witness for complex numbers, not at all. Now, what I was just starting to explain, like by decorating the spiders with numbers, that's like introducing the phases of your block sphere. And that introduces your whole complex circle implicitly. So it's in this picture that they come, the complex numbers. So, okay, let me just tell this story now. So what I've been explaining until here, just with the green and red spiders, doesn't give you universal level language for quantum. You need these complex numbers, of course, to express any matrix. So you need these decorations, and then the rule is just that these phases just add up. So it's still very easy to work with. It's not more, and it's now a very expressive language in which you can articulate any quantum, any matrix, any quantum operation, everything. Now that's not at all the strongest theorem we have. This is what's called universality. Can you express in logic that if you treat this as a logical formalism, can you express everything in your model? Your model is Hilbert space. These spiders are your logical model, your reasoning model. And with this addition of these phases, you can express everything in your Hilbert space language using your logical model. So everything is there.
Mm-hmm.
But of course, reasoning with a system like a logical system is not just about representation, it's about reasoning and the derivations and the manipulations you can do. So I explained one rule about the interaction of two color spiders. There's another one. Basically, there's a rule about what do you do with a square. So on the left, you see a square made up of red and green alternation. Then you can actually write this thing on the right. There's one more rule that you need for the color spider. What do I mean by needing? And that's the main result. I write this as an equation between von Neumann and this. Any equation you can derive, so any calculation, any derivation, every logical manipulation, whatever you want to call it, that you can derive with the rules I just gave you. Everything you can derive in Hilbert space, you can derive with the rules I just gave you.
Mm-hmm.
So this means for equational reasoning, this diagramic formalism equivalent to the Hilbert space formalism. That's a highly non-trivial theorem.
Mm-hmm.
Highly know that it's something we didn't even want to conjecture because we thought it was not true.
Mm-hmm.
And then suddenly some of my former students in a few stages, they proved it very remarkably.
Could you show the square again, please?
Yeah.
Yeah. Okay. So what's the rule?
When you got a big diagram and you find a square somewhere like that, you can substitute it with the thing on the right.
And what does it mean to cross two wires?
Nothing. Ignore. It's just like crossing two electricity wires. You don't care.
Mm-hmm. Okay.
You don't care. That's what technically means that it's a symmetric monoidal category.
Mm-hmm.
You don't care. It's not like a braiding. It's not like that.
Mm-hmm.
You don't care.
Okay.
It's just like, yeah, you don't care. It makes
Bob,
no difference.
I think, Bob, people might mistakenly get the idea that it is connected with the braiding by the fact that you do have this, what appears to be a crossing and
maybe
and under operation.
Maybe I should just have written them going through each other.
Yeah, I think that would make it clearer. Yeah.
Because of course,
it would remove the possibility of making that mistake.
We explain these things in detail in the book, but
sure.
It's for
yeah.
I didn't want to go into too many like
No, I understand.
of
To be quite
the.
honest,
So
I'd made that mistake when I first saw that diagram. I assumed
yeah, I mean,
something like braiding involved
when
here.
you say it, yeah.
Particularly since, of course, there is a role for braided monoidal categories in all of this. But
Yeah, but in this case, it doesn't matter.
no, okay.
It's a symmetric thing.
Thanks for that clarification.
Yeah. Anyway, so the main statement is like for equational reasoning, you can do as much with the pictures as you can do. And we have proven this in all dimensions now. And for also exponent, for also this calculus with exponentiation, all of that. This is technically called a completeness theorem, just to cause even more confusion. It's logical completeness, which means whatever you can do in your model, you can do in your axiomatization or your logical calculus. You can do it out there too. So that's a completeness theorem, very important. Going back to 2018, 2019, I think. And as I said, like the only thing you don't find in this book, in this one, which you find in the one for the kids, is this statement of completeness because we didn't know it yet. It's a bit of a shame. That was really a shame. The book came out and a month later, somebody proved that, which is a little bit of a bummer. We discussed the problem, we discussed the issue, and we say, okay, this is an open problem. And then they tell, okay, you have to do like a second edition. Oh dear. Just as a this is now very wide spread used in quantum computing industry, all this stuff. It's not just an educational thing, it's a very useful thing for so many things. In quantum computing, I don't know how many people here are familiar with the field, so I won't go in details. Very soon you can just get them from us, basically. All the resources, our lectures, our exercises, we can just send them to you. That's not a problem. But we want to get them in like a good place before we like officially announce them. And there has been a little bit, I mean, I can say the discussions are going from, a lot of this work was done under the umbrella of Quantinuum, but it's maybe not ideal for this to be hosted by a commercial organization to start with. And there are some very recent developments. I can't say it yet because it's not entirely official. There's going to be a very, very good venue where they're all going to be available publicly, and whatever else we produce, like extra teaching materials, like Frank asked about. So that will soon be widely announced. I mean, we're already long in, so maybe I shouldn't go in the AI stuff. Maybe I'll just ask what people want to discuss.
Yeah, so should we open it for discussion, Bob?
Yeah, totally.
Yeah, so Michael, we should, of course, thank Bob for a very fascinating insight. I did not know
Absolutely agree.
I didn't. Yeah. So talk is open for questions, please. I think there was some comments earlier. Elona, if you want to say something, please. You have many comments. If you would like to say something, go ahead. And George Sparling had earlier commented that Roger Penrose attributes the diagrammatic tensor notation to Arthur Kelly.
Oh,
yes, it could be.
that's the first time I hear it, but yeah, that's very interesting. Thank you. I mean, I didn't know that because it's universally now called Penrose notation. So that's interesting.
Okay, Cole, go ahead, please.
Hi, Bob. Great talk.
Oh, hello. Long time no see.
Yes, yeah, very long time. Just a quick question. What about introducing relativity, like Lorentz transformations? Like what are the prospects of introducing relativity?
Oh, so basically, if you look, okay, let me go back. I mean, if you look, oh dear, here, I mean, you could think of this as a spatial events. So
Yes.
you've got a little hard event, and then from that, something, maybe some signal is sent to the spade, and then from spade to the. You can think of this as like events in space-time if you want to.
Yes.
And then basically there is a representation of these things as a just a directed a DAG, a directed acyclic graph. The only difference is that you got these boxes which you can think of. Okay, they represent what's happening at the nodes of the DAG. Just then there is one axiom which I didn't give you, which we call causality, and so you can already understand in what direction this is going. It's a very simple diagrammatic property, which unfortunately I don't have ready in my slide, but it's like you take a box, and I'll try to explain. You take a box and you discard the output. So you got a process and you discard what's coming out. And then you say this is the same as not doing the process and discarding what's coming in.
Mm-hmm.
Which is, I mean, this is not connected to anything else. This is just one process. So you do something and then you forget all about what you did. It turns out that if you impose that axiom on diagrams like that, then for free you get things like an abstract equivalence to general covariance, no signaling, and all the sort of things you associate in this kind of process view with relativity theory.
Huh.
You don't get yet the concrete Lorentz transformations or anything like that. But so the fundamental property of not being able to signal, not to be able to, yeah, I mean, general covariance that whatever fluctuation you make, it doesn't matter. The properties of your system stay the same. They can't be fluctuation dependent. Those are already consequences from the simple principle I gave. We discussed it in both books. Even
Sorry, did you say that the no signaling, you would be able to prove that?
Oh, no signaling proof is very simple.
With what you already have?
Yeah, well, no, the extra thing I said.
With the extra thing, okay.
Yeah, you prove no signaling and it's a baby proof. Very, it's one of these proofs that's so simple that it's hard to understand how this match. But you find them in each of the books.
Yes.
Those proofs.
Yeah, excellent.
The covariance is only in the big book, because that's a little bit harder to explain if you don't already know relativity theory of what's the implications of that.
Huh.
But yeah, so there is a shadow here of, I would call there is already a clear shadow of relativity theory without the quantitative explicit content of Lorentz transformations.
Yeah.
But there are people who are specifically working on quantum field theory versions of this and things like that. I mean, as you may know, Carlo Rovelli and myself, and then people like Shaslav and Lucian, we've had this network quantum information structure of space-time for a long time. And the reason they got meaning specifically because of this relativity bits being in here. I think I got a paper about that. Terminality implies no signaling or something. It's a very short paper where I proved the no signaling. And yeah, terminality implies no signaling. Yeah.
Nice, thanks.
Thank you. More questions, please? Bob, I'm still trying to understand, we'll say if we want to teach quantum mechanics at an early stage, but we also want to give them the full picture, by which I would mean, let's say, something like Feynman Lectures in Physics, Volume 3, Quantum Mechanics. It also tries to do a good picture level kind of job to some degree. But coming back to my question, how do I tell a student how to calculate the energy levels of the hydrogen atom and the spectrum? I want the Balmer lines and all the spectrum.
I mean, there are just, I mean, like for example, if you think about quantum algorithms, some of the important ones, even their formulation, like the formulation of the question, goes beyond what you can really explain a young person. Like you need to already know some number theory, like about factoring or something like that, and the properties of the difficulty of factoring to even state the problem for a Shor algorithm. So these things, of course, are, because the problem itself is already challenging in its formulation, it's harder to explain them to younger people. And so there is, of course, a restriction in the sort of things you want to explain, to the extent that the question itself can be grasped.
So what I'm thinking, Bob, like suppose you take your book, Quantum in Pictures, which is of course wonderful, but do we give them a word of caution that this is not all of quantum mechanics? Later, you will.
I would definitely say that. I mean, it depends what you call all of. The way we, I mean, that there are now quite two different cultures, even among physicists. There is like the thing which came out of quantum information, which, I mean, a lot of quantum information, you don't really explain the Schrödinger equation. You say, and that's actually what von Neumann did, by the way. You say evolution is unitary. And you can, and this is how we represent unitary processes. You don't directly, so the way, whether you want to bring in like forces, concrete forces and stuff like that, that's like a different thing, which say electrodynamic forces, something like that. That's actually bringing in a different field in abstract quantum mechanics and trying to like represent it in there. So then the question you have to ask is, to which extent can you explain? I mean, electromechanics is not an easy thing to explain, even in simple terms. I mean, you can. I mean, they know what a magnet is. They know what electricity is. If they put their fingers in the socket and stuff like that. But like the real intrinsic is. I mean, maybe else somebody should do something like this, and people have tried to make like simple pictures of that. And maybe there is a way to make a nice story there of bringing them together. Maybe there is.
Yes.
I think some of these, like for example, relativity theory, people always felt that it was a little bit easier to explain. I don't mean like become like familiar with in really like an intuitive sense, but a sense, but the idea of like, okay, you got a light cone, and you can't go faster than light. I mean, that's something I think I was explained when I was 5, 6 years old. I mean, they explain like, when you say something here, then the person there will hear it later than you say it. I mean, I found that shocking. I honestly found that fact shocking. That sound takes time. It was very, very weird to me. And then when they said light takes time, it was even more shocking. And so so I think what we have here is really the abstract framework of quantum mechanics. Whenever you talk about Schrödinger equation, you typically bring in other features.
Forces,
and things like that. And you can do this, but to do this with young people, that's maybe not the right thing. Like one.
I was just thinking.
I totally understand the question.
How to tell the young people in a clear way that this aspect is what we are teaching, and this aspect you will learn later when you learn about forces.
Yeah, something like that. Something like that would be a good way. I mean, it would be nice to have a nice way to say that. Exactly what you say.
Yeah, I agree.
That's what you. And I totally get that.
Thank you.
It's of course the case now that, I mean, when I was taught quantum mechanics, which must have been, trying to think now, maybe 1988, 1989, it's a very different thing from whatever you would get now, because so many new things were discovered. I mean, starting with like first quantum crypto, then things like quantum teleportation, which are all very fascinating phenomena, which interface also with space-time. So one of the things we chose to do, to some extent in the book, is the interface with space-time, because it's quite intuitive to explain. Alice is on one planet, Bob is on another planet. They try to share something. These are things kids understand. You don't need to know.
I agree. What I'm thinking, Bernd will come to in a moment, please, if you don't mind. See, for example, I'm working on the following problem. For me, quantum non-locality, the way Alice and Bob are able to sense each other outside the light cone, even though there's no signaling, the EPR paradox, for me, that's a problem. There's a conflict between relativity and quantum mechanics. And we work on trying to understand, could it be that in some more general space-time, the communication is actually local? It's not outside the light cone. In a more bigger space-time, it is inside the light cone. So I'm thinking of we would like to impress upon young minds that this is actually a problem.
Sure. Actually, I mean, one thing we have to give an example of something sophisticated that we have in the book for the kids is the proof of quantum non-locality. It's there, so just with diagrams. So the way we say it is that something seems to happen, places far apart, which should not actually be able to communicate with each other.
Yeah.
There is some sort of correlation which emerges. we don't use these words. We change our words which we use, of course, to work.
I'm tempted to mention a solution we have proposed, that the universe actually does not have just one time and three spaces. It has three times and three spatial directions. And in that 6-dimensional space-time, actually everything happens nicely. In the sense, it's consistent with relativity, no outside the light cone influence. But because we don't observe those extra times for certain reasons, it looks as if in our 4D space-time, something funny is going on.
So, I mean, you may enjoy the fact that there is kind of also some kind of solution like that implicit in the way in our pictures. Because of course you can see how the information through the pictures goes from one side to the other. It's almost like there are some entities which are allowed to do stuff which most stuff don't.
Okay, I'll send you my paper and I'll see your book. Very interesting. So
because you can in our proofs of non-locality, we prove the 3-particle non-locality GHZ, which is more difficult in Hilbert space, but actually for us is more easy.
Okay.
It's qualitative argument, and then you can effectively see that some of these spider phases they just move back in time, and they do things, they break causality to some extent, as if there is some special channel, some special wires which these things are allowed to travel in.
Yeah, I call that the quantum wormhole.
So it's something like that. I mean, it's like a wormhole almost.
Okay, great. I think
not everything, but something can go through.
We should discuss this more. Yeah, only quantum particles can access that extra channel. Classical.
I wouldn't even say particles. It's features. Features.
Yes.
It's certain features are allowed to do that, but not the whole state.
I agree. Yeah. Yeah. Thank you. Thank you. Bernd, please go ahead.
Thank you for the nice talk. Enjoy your drink before I start asking. One, more simple. Well, I don't know whether it's simple, but has this also already been applied to quantum field theory? So it's a follow-up question to relativity.
Yes. So there's quite a few papers by former students of me. One is by Stefano Goggioso, who's my co-author of the kids' book, and Fabrizio Genovese, and they have a series on papers on really by using non-standard analysis, motivating these diagrams in like field theory regime where everything diverges and stuff like that. And then you can basically start using the same pictures. The idea is to connect these pictures then to a model.
Okay.
The model would be like a field theory formulated in non-standard analysis. I know like Stefano is now doing something else, a different approach to the same problem. We have a guy called Razin Shaikh. I don't know even if they have put their papers out, but like Stefano is a person who's done quite a lot on that specifically. So if you would just write him, then he provide you with some references.
Then I can ask.
He's done quite a bit in that space.
Okay.
I mean, I should say like when people like Attia, who you may know, and then later people like John Byers started all to do topological quantum field theory, these diagrams were very similar. So they were, of course, abstracting away a lot of field theory, but they were working with these when they have these cobordisms and all of that, they're the spiders. Those are the spiders. But they, of course, don't have a universal language because they abstract so much away. They only care about the overall topological space, structure of spaces, but they were already the same structures.
Basically, I now have a new question I didn't have before. But anyway, so is there also a link to quantum groups?
Yeah. I mean, I didn't want. At some point, I even mentioned sort of quantum algebra, but
yes, algebra. You did, but
like
not
this
groups.
equation. This equation. Usually, people write it differently, but that's one of the defining equations of a bialgebra.
Ah, okay.
That's one. I mean, I've got it somewhere on the slide. If you look at here, the way you see it there, it's not a square. It's like a bow tie, twisted square.
Okay.
This is what you would find in your typical quantum group theory papers. Like this is the defining equation of a algebra, of quantum algebra, and the one here, where the two wires go away, this looks very much like a Hopf, like what the equation of Hopf algebra, where you would have an antipode typically. On one of the wires, you would have an antipode. Now here, the antipode is just trivial.
But
If you go to three-dimensional space, it won't be trivial. For qubits, it's trivial. In three-dimensional space, it won't be trivial. But you got the structure of a Hopf algebra sitting here.
okay.
But you got more. But you got more. The point is, you couldn't do what we are doing with a Hopf algebra alone.
Okay.
Because you don't. What you don't have is this. You would have a monoid and a commanoid, and this, and they make this is what's called the Dagger special commutative Frobenius algebra, which is like your monoid commanoid part with a lot more structure.
Okay,
and you do need that. You do need that.
The Hopf algebra is discussed in your book?
No. I mean, I think it confused people. I mean, there was for a long time when we were publishing these papers, so much confusion among referees that they thought, okay, you guys are working with Hopf algebra. That's all you're doing.
Okay.
And then no, that's not it. And then they were too arrogant to basically admit that they were wrong. And then suddenly Sean Majid, who's the biggest name in the
Godfather of quantum groups.
he started to basically work on this, and then said, because this is really new and really interesting. And then they suddenly all realized, oh dear, we were wrong. We were all completely wrong as a community. There is something more here because Sean now says it.
Okay, so the Pope of quantum groups had to say.
Oh, he he has a bunch of papers now on this, on ZX calculus specifically, because he did a sabbatical with us, at Quantinuum, to learn stuff better after he realized, I mean, on the one hand, he said, with all I've done in quantum group theory, of course, I'm sure I can contribute here. But on the other hand, he realized that this was different. That it was more.
Oh, different, but maybe this helps. So quantum group theory also has reached its limits when it comes to physical applications. So maybe this was too narrow.
It's really not having the ability to bend things up and down.
I'm
they're commanoid, and they're very fixed in place. Here
Okay.
you can just bend legs up and down and in all directions, which is an ability you don't have.
Okay, so your formalism is less rigid compared to the
less rigid.
Okay, this is really interesting. So looking forward to future developments, and we'll have a look at Sean.
I mean, like I said, there's quite a lot of work already. On the one hand, there are some papers by Sean Majid. On the other hand, people in classical computer science, so they don't do these decorations with phases. They have been starting to use this to prove a hell of a lot of stuff about like classical processes, about reasoning about relations, and because you can learn. And that was a good question, which Tjander like asked at the point, like, hey, Bob, is this about quantum or classical? A lot of people have basically thrown away the quantum part here and then started with this system prove a lot of useful things about computer science.
Interesting. Can you tell us more about the throwing away the quantum stuff? Do you have maybe
throwing away the quantum stuff? I would say you basically just throw away these phases. Where are they? Oh, sorry. These decorations, these angles.
Decoration? Oh, okay.
A lot of the calculations I did here, I didn't use these angles. Where are they?
Okay, and this would be my final question.
These. If you throw them away, you still have an interesting system.
But it's no longer quantum.
I mean, you don't have the complex numbers, so you don't have any of that.
Okay, and I promise this is my final question. Now, I talked about getting from quantum theory to classical theory. Let's now go in the opposite direction to more general theories, because this is a series on the octonions, so on special ideas to go to a non-associative kind of generalization of quantum theory. Is this something which could be done, or could you use category theory to have a kind of overview, how do you call it, bird view of different possible extensions of quantum theory?
I mean, I can't say anything I know people have been looking into to trying to get similar structure, at least get them non-associative and all of that. I mean, the way this works is there's a guy, for example, Rob Speckens, who made a system which is very similar to quantum. He called him a toy theory or something like that. And for example, the way you get this toy theory out of here is, you see these decorations I'm putting on the spiders. Now, instead of putting like a circle, like the whole complex numbers, you just put like 4 points. They call it stabilizer. So like just 4, the group Z4. Then you get what's called stabilizer quantum mechanics. If instead of the group Z4, you put the group Z2 times Z2, then you get Rob Speckens' model. It's about how you decorate the spiders. When you do, and then we were talking earlier about non-locality proof. So you prove non-locality, you don't need all the complex numbers, you just need the Z4 structure. If you replace in that proof the Z4 structure by Z2 times Z2, and the proof just, the whole calculation stays the same, then you see that at the end your contradiction vanishes. And you lose non-locality by going from Z4 to Z2 times Z2 as a decoration. Now, I don't know, I don't think that anybody has ever tried to decorate the spiders with octonions. And maybe Cole should do that.
So far, nobody has tried.
But I think there is something to be learned from trying to decorate them with octonions without making your whole system non-associative. Because it's really about these phases to be non-associative. So I think it could be possible. I think people have tried with quaternions. Now I remember people have tried with quaternions, I think, but not octonions.
That's why I'm thinking, the picture language seems powerful enough to try to proceed towards non-associative quantum mechanics. I agree with Bernd. Also, the other thing I wanted to ask was...
thank you for answering my questions. Sorry.
No, you go ahead, Bernd. You finished? Go
ahead. Yes, I'm finished, and I wanted to thank him for answering all my questions. And now you can continue.
Thank you. So I want to, you suppose, try to use this to solve some problem in particle physics or quantum mechanics, which is not getting solved in the traditional way. Just take some example. Why is the fine structure constant 1 by 137?
Oh.
Yeah, so I'm trying to understand how far is the reach of the picture method?
I mean, I can't predict that. I know, I mean, for many reasons, not in the least careers of people, like a big focus has been on things related to quantum computing. To give one example, which I think is maybe interesting for more broader reasons, there is, for example, this model called measurement-based quantum computing. In standard quantum computing, you get a state, you apply like a circuit, you do measurements. That's kind of what it is. In measurement-based quantum computing, you build a huge entangled state, and then you start measuring things. It's a completely different way of thinking, reasoning. It was introduced like 2001, 2002 by Rausendorf and Briegel. And it's incredibly difficult, not to say impossible, to do proper computations or get any intuition when you work with Hilbert space. But at nothing. As a matter of fact, the reason we came up with this green-red calculus, I mean, I already had the spiders in one color. I already had that. But the way we found like this interaction in what we call bialgebra, this sort of stuff, was by looking specifically at a problem in that field, measurement-based quantum computing. So that was an important origin to developing this in order to solve problems. And the people who are now doing measurement-based quantum computing is everybody who's trying to build a quantum computer with photonics. Anybody who's trying to build a quantum computer with photons use measurement-based quantum computing, and they're all using this language as their main language, just to do things like error correction and whatever you need to do in the space of engineering. My daughter is very anxious, like screaming at me, because I had to lock her out. But anyway, But yeah, and so in that space from the start, we actually we brought in this calculus to solve a problem. The important other applications is you got a very big circuit, you just want to compile it into a smaller one. This is what you use. Coming up with
Okay.
error correction stuff. Like all the main guys at IBM, at Google, they all use this.
Mhm.
So there's
So
there's so
in
there's
your
a
sorry.
lot of applications in engineering. Like with Carlo Rovelli, we're looking in what can this teach us about like paths to quantum gravity.
Yeah, that's the kind of question I was asking. Yes.
Yeah. And so we soon will have a paper out where we basically are computing things about loop quantum gravity using this.
Yeah, that's the kind of question I'm asking. Very
Yeah,
interesting.
so I mean, I just got it sent to me like the final draft 2 hours ago. So I have to go through it and then we'll publicize it. And it's
Very
about
interesting.
spin networks, and it uses this extended calculus with where you do differentiation and integration, all of that.
And when your original title you said quantum AI, you mean the use of such pictures?
Well, let me just keep it because I actually have a meeting at 5. So I will start. So this is something which happened in around 2006, 2004. So I didn't show a picture of teleportation, but I've got a picture about teleportation. That was actually the first thing we came up with, like in 2004, using this, or 2003, these pictures. And I was giving a talk in McGill. McGill was mentioned earlier by Mike, category theory seminar. And I was presenting quantum teleportation in terms of these pictures, monodal categories, whatever you want to call it. Jim Lambeck was in the audience. Jim Lambeck, one of the fathers of mathematical linguistics. When he saw this picture of teleportation, he said, Bob, this is grammar. I said, no, Jim, this is physics. He said, no, this is Bob's grammar. And it turned out that this was again, if you go in to your category theory abstraction, this was exactly the same structure he was using to formulate grammar as we were using to reason about things like teleportation.
Mm-hmm.
And the result of that 1 or 2 years later, in a collaboration with 2 people, Mernush Chaudhry and Steve Clark, was that we came up with an algorithm, if you want, on how to compute the meaning, I'm talking about meaning, not grammar, of a sentence given the meaning of its words. So the meaning of the words are vectors, as we all now know. You got some linguistic structure, and then you want to compute the meaning of the whole. And like this structure was actually exactly through this kind of diagrammatic quantum formalism, the way to find the meaning. So in 2020, for the first time, we did quantum natural language processing on a quantum computer, a small one, using this structure, which would be impossible using just data-driven stuff, which everybody is doing today.
Mm-hmm.
And our main approach now, well, let me just put on a slide. So our main we've got a blog post about this sort of stuff, talking quantum circuits. You see these pictures. It's about reasoning about quantum circuits, and this allows us to basically come up with new ways to do AI, responsible ways, which are all about like interpretability, scalability, and we demonstrate this stuff experimentally, of course. It's all experimental work. I couldn't get there now in the talk. Wait, I couldn't get there now in the talk. But so there's a blog post. If you are interested, you can read. And so effectively from these pictures, you end up with a new approach to AI.
Mm-hmm. Okay, great. Thank you.
That's a direct line. That was a direct line.
Mm-hmm. It's great. Yeah, I think you have a new meeting coming up, so we should.
I mean,
find
last year, like in the quantum computing media, so to say, this result was like selected as one of the 10 biggest achievements in the whole space of quantum computing progress. So,
wow, great. Yeah, it's definitely been an eye opener, certainly for me. Michael, please go ahead.
Well, I'm not going to add anything except to say thank you, Bob. A wonderful talk, and I think it was an eye opener for a lot of people. Very, very unlike the talks we've had on OSMU typically, but in the sense that it's been very thought-provoking and generated tremendous amount of feedback. It's very much in the tradition.
Yeah, I would put it in the language of revolutionary, I think.
Yes, we're revolutionary, exactly, which is exactly what we are. And more power to your elbow. And I look forward very much to seeing you on the 30th.
Oh, yes.
The memorial for Basil.
In UCL, yes.
Yes, I'll see you there.
Okay. Thank
All the
you.
best, and thank you again a million for coming and giving this talk.
Bye, everybody. Thanks, everybody. I have to rush
Thanks,
now.
Bob. Thank you.
Bye.
Bye.